Functions. All right, so the first thing that I want to talk about here when we introduce functions is just some sets of numbers so that we can talk about, because we're going to talk about builder notation and stuff like that. And so it introduces talking about sets, and these are hopefully familiar terms to you. Natural, whole, integer, rational, irrational, and those are all real numbers. If you'll recall, natural numbers are your counting numbers, 1, 2, 3, 4, 5. Whole numbers have 0. Integers, throw in your negatives. Irrationals are ones that are non-repeating, non-terminating decimals. Rationals are your terminating and repeating decimals, and they are all real numbers. We have dealt with imaginary numbers when we did but these are all going to be real numbers for right now. When we introduce imaginary, we'll talk about it more then. But sets of numbers. So the first thing we talk about is, how do I write sets of numbers? The reason this is important is because when we go to functions, you have to be able to tell me like an answer, and it could be a huge sets of numbers, and you have to be able to tell me what you're defining. And so the first thing that they talk about to define sets of numbers is using what's called set builder notation. Set builder notation. So this notation has these little squiggly brackets here. See those? The variable here, that's just telling me that you have a set of numbers that you're going to define. Then you have this line here. It looks almost like an absolute value line, but what it actually means when you interpret are the words such that. So this is saying all x such that, and then after that, you're going to define what that means. Such that x is between -3 and 16 inclusively. So -3 is less than or equal to x, which is less than or equal to 16. And you're telling me that x is an integer. This part's important because if you just gave me this, then I would think you could have 0, 0.1, 0.2, 0.3, 0.5, 0.6, 0.7, right? If you just gave me this range here and you did not define it this way and say, hey, I'm just talking about integers, then I would think it would be every decimal or every real number in between that infinitely, okay? By giving me this piece, then I know it's just -3, -2, -1, 0, and so on and so forth. All right, so all they've done is they've just defined a set of numbers using set builder notation. Set builder notation. So let's look at some examples of just writing things in set builder notation. Look at example 1. Describe this set using set builder notation. So we are going to set it up just the same way that we did the other one. We are going to use this little bracket. We're going to say, x such that. And then what do you notice? We have 8, 9, 10, 11. What do you think the next number is going to be? 12. So we know that x is going to be some number greater than or equal to 8, right? Based on what they've given us. So x is greater than or equal to 8. Does it look like they're including decimals and fractions in between those numbers? No. No, it does not. So we are going to define this by either natural, whole, or integer. We can any of those based on greater than or equal to 8 is going to be valid. They actually used whole numbers, but you could say, x is a natural number. Or you could say x is a whole number or x is an integer. As long as you're telling me, hey, I'm not talking about the decimals in between there. All right. So let's look at B. X is less than 7. Does this include decimals? Yeah. Yes, because it just said less than 7. So for this one, I am going to do set builder notation again, just like I did before, with the little bracket, with the x, with the little such that. X is less than 7. But in this case, I'm going to just say it is a real number. It is a real number. Because apparently it can be decimals based on what they gave me. All right? Let's look at the last one. The last one's a little different. All multiples of 3. All multiples of 3. How do you get to multiples of 3? How do I get to 6? How do I get to 9? How do I get to 12? You have to multiply by 3. So you have to multiply some number by 3. So for this one, you're going to say, well, I'm going to have all the x's such that x is going to equal 3 times a number. A number has to be an integer, right? To be a multiple, it has to be evenly divisible by 3. So n would have to be some integer, meaning it cannot be a decimal. It has to be an integer. That is set builder notation. So go ahead and try guided practice 1, A, B, and C. All right, let's go over these. The first one, 1, 2, 3, 4, 5. For this one, x is an element of the natural numbers, and it is greater than or equal to 1. So just x such that x is greater than or equal to 1, and x is an element of the natural numbers. Because natural starts with 1, you could have, if you wanted to, just done this piece of it. That set is defined by that. That is your natural number set. All right, for the next one, x is less than or equal to -3. So we have x such that x is less than or equal to -3. And for this one, they have integers. I would actually have used real numbers there because they did not tell you that it was just integers. So for this one, I disagree with the book here, and I actually said this last year too. I would have actually done this right here, real numbers, because they did not tell me that it was just whole numbers and their opposites here. All multiples of pi, this is going to look just like 3. X such that x times, or pi times n, and n is an element of your integers. No, n is an element. Why did they have an I there? That's irrational. That should be a z. Okay, yeah, I disagree with the book here too. I disagree. Yeah, that should be a z. Pi times n is going to be an irrational number, but your n is not an irrational number. That is going to be in your integer set. As you're going through these, just pay attention to, does it include it or does it not include it? And so if it includes it, we're going to include this bracket. If it doesn't, we're going to use a parentheses here. So for this first one, -8 is less than x, which is less than or equal to 16. My endpoints here are going to be -8 and 16. Does it include -8? Does it also include it? No, so I'm going to just use parentheses. Does it include 16? Yes, so I'm going to use a bracket. All right, let's look at this one. It is less than 11. So I have 11, and everything less than 11 I'm going to represent with negative infinity. That means it's going to go on negative in an infinite direction. All right, infinity is always parentheses. We never put a bracket there. Does this include the 11? No, so I'm going to put parentheses there too. All right. Now let's say I have this statement here with like an and or an or, okay? And or an or. If you have an and or, you're actually going to use your union and intersection notation like we did from the last chapter. All right. So for this one, I'm going to do this interval notation. X is less than or equal to -16. Remember, with less than or equal to, I'm going to use a negative infinity. So I'm going to say negative infinity and -16. Infinity is always open. Does this include -16? Is it inclusive of -16? Yes. So I'm going to use the brackets there. And then what is my symbol for or? Or. Maybe this will help. Or is union, and is intersection. So I'm going to use the or symbol there. All right. And then x is greater than 5. So anytime I'm going greater than, I'm going to use positive infinity. That is a parentheses there. Does that include the 5? No. So I'm going to use parentheses there too. All right. So that is interval notation. Set builder is when you use the little squiggly brackets and you have x such that, and you just define it. Interval is where you actually give sets of numbers based on the starting and ending points of those sets. All right. So go ahead and try guided practice 2 there. Guided practice 2. Write those in interval notation. Interval notation. All right. So let's look at these. -4 is less than or equal to y, which is less than -1. You should have had -4 and -1. Bracket on the left, parentheses on the right. A is greater than or equal to -3. -3 in positive infinity, bracket by -3, parentheses by infinity. And x is greater than 9 or x is less than -2. You should have had negative infinity and -2, both with parentheses. Union 9 and infinity, both parentheses. Start talking about functions. Functions have a specific rule. Functions are a relationship between two things, between input and output. But there is exactly a one-to-one relationship from your input to your output, or from your X to your Y. All right? So I relate it to like scanning your own groceries. If you have a barcode for a loaf of bread, no matter how many times you ring that barcode, it should give the same price. That is a function, right? Now, it doesn't mean there aren't other things that might cost exactly the same, but that barcode should only yield one price. If you were to scan the barcode and it's $1 this time and it's $2 the next time you scan it and it's $1.50 the next time you scan it, we have a problem, right? So, if there is more than one Y or more than one range from your input, from your domain, then there's a problem. It's not a function. Now, it doesn't mean that you can't have X's going to the same Y. If my loaf of bread costs $2, every time I scan it, it should cost $2. It doesn't mean that the box of cookies cannot cost $2, right? That's okay. It just means that every time I input that specific barcode, it gives me the same price. Same is true of a function. For if you have an X, it will only yield one answer. It doesn't mean multiple X's cannot go to the same Y. That's okay. But the X will always only yield one answer. The way that they have it up here is called a mapping diagram. A mapping diagram, this is one way to tell if something is a function. If you look here, they've listed all of my domain, all my X's here, and all of my range, all of my Y's here, domain and range, all right? They actually put 7 in here because they did from 6 to 9, but if you'll notice, 1 goes to 6, 2 goes to 8, 3 goes to 8, 4 goes to 9. This is a function. Every one of these gave me only one answer, okay? If I had 2 going to 8 and 2 going to 7, this would not be a function, okay? It has to be one-to-one from your domain to your range. All right, the next thing they look at when you're testing to see if it's a function is vertical line test. It's the top of page 6. For any function, whether it is a graph or whether it is just dots on the coordinate plane, you should be able to draw a vertical line anywhere on that and only cross it at most one time. It doesn't mean you have to cross it. I mean, there are places where I could potentially draw a line and not cross over it. That's okay, but I cannot cross it twice. If I cross it twice, it is not a function. What that's telling me is I have an X with 2 Y's somewhere on that coordinate plane. All right? So the first thing they want to do here is they want us to tell them, is this a function? So let's look at these. The input value X is a student's ID number. The output value Y is the student's score on a physics exam. Is that a function?
Yes.
Why is that a function? This first one is a function. The input is the student ID number. The output is the grade. All right, what about B? Is this a function?
No.
So -8 gives me -5, right? -5 gives me -4. 0 gives me -3. 3 gives me -2. And 6 gives me -3. This is a function. It does not matter that these aren't. You were looking at this one. It doesn't matter that these are duplicated. It only matters that this only gave me one answer. What about C? No. Vertical line test fails here. Okay? What happens when we have a function that just looks like this? How do we know? So what we do here is we do what we did on bell work. We get the Y by itself. Okay? And so we're going to get Y by itself. We will add the 2x over. So we'll have Y squared equals 2x plus 5. And then how do I solve this? Well, I have to take the square root of both sides. Y is going to equal the positive or negative root of 2x plus 5. What's the problem here? I'm going to do an input of, let's say, let's say x equals 15 here.
You're gonna get
10. I like 10 better. So let's say x equals 10. All right? I should get one and only one y, right? I plug in a 10. I get the positive or negative square root of 25, which is going to be what? 5 or?
-5.
I have a problem.
You cannot do it.
I have 2 outputs, right? So no, this one is not a function. When you solve for y, you should only have one answer that you can get. Now, the x can be squared, but when your y is squared, it causes problems because then when you solve for it, you have the positive or negative root, and that tells you it's not going to be a function. The input value is the area code. The output is a phone number. Is that a function? No, because there's a whole bunch of phone numbers linked to the one area code, right? What about B? Is that a function? No. 5 yields 8 and 5 yields 9. This is not a function. All right, let's look at C. Is this a function? Yes, this passed the vertical line test. And what about D? If we get y by itself, is this a function? Yes, it's just an actual linear function here, right? That is a function, all right? So this is also really simple. Notation is a little different, but this is notation that we learned in Algebra 2. Evaluating a function is literally just plugging in and doing order of operations. That's all it wants you to do. So if it says, I have given you this function here, g of x equals x squared plus 8x minus 24, and they want you to evaluate it, what is g of 6? They literally just want you to plug in a 6. So g of 6 is going to equal 6 squared plus 8 times 6 minus 24. And so you're going to get what? 36 plus 48 minus 24. You're going to get 60 there. You're just evaluating. You're just plugging it in. What happens when they tell me to put negative 4x in there? Well, that is just going to be negative 4x squared plus 8 times negative 4x minus 24. Don't forget, by the way, when you do this guy, that you have to square both of them. Negative 4 squared is 16 and x squared minus 32x minus 24. I cannot combine any of those. That is my answer, all right? And then when they throw even the bigger one in there, 5c plus 4, if you were to have to do this guy, FOIL him, distribute here. And then when you get it all done, combine your like terms. All right, so this notation just means plug it into the function. Plug it into the g function there, or into the f function, or into the h function. Whatever the function is they gave you, they just want you to plug it in. All right, and then do order of operations. So go ahead and try a guided practice just for A and B. Just A and B there. All right, so domain is the input. It's the x value. And when it says finding the domain, what it's asking you, is there anything that is limiting what you can use when you plug in an x? So is the domain just all real numbers? Like y equals mx plus b is a good example. If I have like y equals 3x plus 5, I can literally use any number from negative infinity to positive infinity. And none of it causes a problem. And so my domain would legitimately be all real numbers. X is an element of real numbers if I were doing like my set notation. All real numbers works for that. There's no limitations. So you have two types of domains. You have an implied domain, which is what this is, and you have an explicit domain where they just hand it to you and say X has to be these numbers, okay? When it just doesn't like the way it is on this example, it is an implied domain, meaning the function itself implies limitations on the domain. For A, you have an implied limitation because something in that denominator would cause a problem. What causes a problem in the denominator?
Square.
0. 0 causes a problem in the denominator, right? It doesn't matter that you have an x squared. It matters that it can't be 0, right? Why can't it be 0?
Because
It can't divide by 0, right? And so when I have something like this, I am going to assume, based on that function, that there are going to be limitations. The limitations are whatever makes that denominator 0. So how do I find it? Set it equal to 0 and figure out what it is, okay? And so I am going to set this guy equal to 0, and I'm going to say what's going to cause a problem. The easiest way to solve these is to factor. I can take an x out. X minus 7 equals 0. If I have two things multiplied together to get 0, one of them has to be 0. So either x is going to be 0 or x minus 7 is going to be 0. So I know there's two numbers that could cause a problem. 0 can cause a problem and positive 7 can cause a problem. I know that x cannot equal either one of those. That is my domain. So if I did it in set builder notation, I would say my domain then is all x such that x is not equal to 0 or 7. That is my domain of that function. All right, that's my domain. Now, if I were going to do that in interval notation, it's a little weirder. You would say from infinity to 0, union with from 7 to infinity. What I'm saying, and then actually one more union in there. We got to do from 0 to 7, 7 to infinity. So for these, I actually prefer set builder notation because the interval's weird because you have to really say from infinity to 0, not including 0, 0 to 7, not including either one of those, 7 to infinity. So you're basically just saying any number except 0 and 7. What about b? Are there any limitations when I have a square root? Right, it can't be negative. So for this one, I actually need to find out where it's 0, and it can't be anything that causes anything less than 0, right? So you would say, where does t minus 5, where is it less than 0? That's what we're looking for, right? Where it's less than 0. That causes a problem. So how do I solve that?
Whatever the t
Just,
value has to be
add the 5 over, right? So t is less than 5, that is a problem, okay? So what isn't a problem? Well, where it isn't a problem is where it is greater than or equal to 0, right? So this would be my domain, is where it is greater than or equal to 5. So if I were to write that in set builder notation, x, such that x, or in this case t, I guess, because they have a t there, t such that t is greater than or equal to 5, and t is really in the real number set because it can be decimals. That's not a problem. What about the last one? The denominator cannot be 0 and it can't be negative, right? So I need this one to be just greater than 0, not greater than or equal to 0, right? Just greater than 0. So where does this happen? Add your 9 over. Where does this happen? Where is x squared greater than 9? It's kind of like absolute value. So we know when x is greater than 3, that's going to work, right? Where's another place where it works? Where's it greater than 0? What about, is that greater than 3? But does it work here?
Yes. So it would be like I don't like this.
So you got to think about this. You've got to think about this. When you have that squared and you're talking about your greater than, less than, okay? You've got to think about what happens when you do a square. It makes it positive. So a 3 squared is going to be, anything bigger than that's going to be bigger than 9. A negative 3 squared, anything less than that's going to be bigger than 9, right? Because when you square it, it turns positive. And so that would be your domain there. So this one's a little bit different when you have a square there. All right, for this, and I'm not worried about the word problem in and of itself. I want you to actually pay attention to this part right here. This is called a piecewise function. This is called an explicit domain. Why is it explicit? Well, because they define it for you. It is not implied. They actually say, when x is between 63 and 66, this is what you're going to use. When x is between 66 and 68, this is what you're going to use. And then when x is greater than 68, this is what you're going to use. You don't have to figure it out. You don't have to be like, well, the denominator can't be 0 and this can't be that. No, it's saying, okay, here is your domain. And here is what you use for your domain. And so if I were to say, what is the value of this function at 67, you would actually go back up here and say, well, which one of these does it fall in? Does the first, second, or third? Where is 67?
It's greater than, no.
It's right here, isn't it?
Yeah.
So for 67, you would plug it in here. And you would actually say 3 times 67 minus 132. You would use that one. What about this guy? Where's 72? In the third one. So for this one, you would actually say 2 times 72 minus 66 to get that one. Okay? So when they have an explicit domain, you use wherever it is that yours falls. And that's the function you're going to use for that. It's called a piecewise function because they basically put multiple functions, they piece it together.